Hello ladies and gentlemen, my name is Roelofs and I'll be your presenter in this session. I would also like to mention my Dutch colleagues, Emons and Verschoor, co-researchers in this study. A full paper has been accepted for the International Journal of Testing. Below you see the parts of our presentation. You can read them yourselves. Item features play various roles in evidence-centered design. I mentioned 4 of them. First of all, to create items that are parallel and equivalent on essential features. Second, task varying in difficulty levels by theoretically relevant task features that change the level of required competency. Third, optimize item discrimination or evidential strength by choosing the features that establish a correlation between the item score and the target skill. Fourth, to warrant that the collection of items spans the full construct. The features more or less define this span. In our research, we concentrate on explaining difficulty and item discrimination by means of item features. The research question was to what extent are evidence-centered design developed item features for driving theory exams associated with item difficulty and item discriminative power? To what extent are the features intrinsic or extraneous in nature? The case for today is the Dutch traffic theory exam. The theory exam has gone through many changes, evolving from a classroom-based whole group test into individual computer-based test. The traffic theory test consists of 2 parts. The first part about hazard perception in traffic is not discussed here. The second part is object of our study. It's about traffic rules embedded in traffic tasks, such as merging, turning, crossing, in traffic situations, such as intersections. This part contains 40 items and the cutoff score for passing is 35 out of 40. For our research, we constructed a task model that describes the solving of specific exam items, namely solving priority order at traffic intersections. Using theoretical insights, we analyzed the cognitive steps of priority tasks at intersections and defined a number of steps that are intrinsic to the task. Because a test item is not an in vivo real-life task, test takers also must take steps that are actually extraneous to the real task, such as dealing with the item presentation, understanding the STEM formulation, and using a certain response method. These require access skills, including reading, writing, working memory, which are not necessarily used in real-life traffic. On the other hand, we describe the task features that are part of each item, including intersection feature, such as the number of crossing roads, the number and then the number of kinds of traffic rules presented, and finally, item presentation features, the type of the STEM, the way to respond. These features are related to the essential cognitive skills, but also partly to the non-focal skills. Through the relation with item difficulty and item discrimination, we come to know more about what drives the parameters and for what reasons. Let me now show you the cognitive steps for solving priority tasks as intersections. What you see here is an intersection with 4 participants. The first step in the cognitive process of solving the order is to determine the relevant actors. Do they actually participate here? Yes, they do. The second step is to perceive how they participate. What are the decisions that they need to make? What are their positions and their intended maneuvers? To cross, to turn left, to turn right. The third step is evaluating whom out of each pair goes first, using different rules and signs. For instance, here are 4 interactions which are solved by different general traffic rules. And these are assigned different law traffic numbers. Other interactions can be solved by reading or using traffic signs painted on the road or posted on the road. The fourth step is to combine the outcomes of each pairwise interaction on this intersection in a kind of mental competition matrix. The matrix could look like this. It shows you all members of this competition between the road users at the intersection, and in the cells you see who wins due to which traffic rule or traffic sign. After completing, you can count the number of wins and decide as a fifth step about the correct order of who's to go first. The sixth step is to infer the answer to the specific question about the order, which includes responding on several types of item stems, such as who goes first, determine the full correct order of priority, determine whether a particular road user in situation will go first, and determine whether a presented solution is legally allowed. The seventh step is to express the answer on the question using the response tool. Look at this item. The question is, which is the correct order? This can be expressed verbally by choosing the right option B. For this situation, out of 3 verbally mentions lists of road users. Test takers can also give a visual response by drag and dropping the right order directly into the picture. We analyzed 353 items on intersection problems. We coded the items on the item features as described, derived from our cognitive model. Then we used 2 years of test data from 200,000 candidates to calculate difficulty parameters and item discrimination parameters using an item response model. After this, we applied multiple regression analysis in which item difficulty and item discrimination were predicted using a set of item features. That brings us to the results. In this table, you see the predictive model for item difficulty. 3 domains of features result in the regression equation. First, we see that intersection features have a meaningful contribution to item difficulty, about 13% of the variance in item difficulty. More specifically, 2 specific features come out as strong predictors. One is that when a user already has entered the intersection and is located on a central space, the item becomes more difficult then. Probably it's more difficult for test takers to determine which rule applies than when the user is still located at the entrance of the intersection. Another feature that comes out, the more often a test taker has to verify his own right of way in judging an interaction, the item is more difficult. Then, traffic rules accounted for 25% of the variance in item difficulty. In general, you can say that the more rules need to be considered, the more difficult the item gets. Third, a very small amount of variance could be explained by presentation features, the way the question was posed to the student, test takers. Overall, 38% of the variance was explained by our set of item features. The next table shows the prediction of item discrimination. We see in general that the intersection features accounted for 80.6% of the variance. Very interesting, again we see the role of verification of one's own right of way. The more often the test taker has to verify this right in judging an interaction with other road users, the higher the evidential strength of the item. Rules and traffic also show a meaningful contribution to item discrimination, 40.1% of the variance. The more rules, the stronger the item discrimination. Finally, it came out that presentation features also contributed to item discrimination, 7.1%. More specifically, the use of a visual response led to a better discrimination than the use of a verbal response, probably leading to less extraneous verbal task load and decreasing the chances for guessing. Conclusions. Because of limited time, let me mention some brief concluding messages. In general, we may conclude that the approach of task features improves our evaluations of item and test validity. We observe that adding theoretically relevant intrinsic task features to items leads to higher item difficulty, and at the same time to higher evidence strength, as expressed by item discrimination. Now we can consider task features as building blocks for systematic item construction that can be communicated among test constructors for automatic item construction generation once the features are part of a generative item model, measuring more complex skills to bring some order in what belongs to the target skill and what can be considered extraneous. Thank you very much for your attention.